I'm going to tell about upcoming feature, which we were waiting for like 10 years or even more, about JIT compilation in Ruby, the sort of optimization of code. So, a few words about me. Some of you have seen me previously on last year's Brook with a speech about Ruby on 32 kilos of RAM memory. My name is Mikhail Bortnyk. I'm a team leader at NIX. Aside of my regular Ruby coder work, I'm doing language researches. I'm third contributor of mruby/C. It's a special version of Ruby which oriented for microcontroller units. And active user of Ruby, C, JavaScript, Erlang, and currently learning Camel. Trying to support and evolve Ruby community, mostly local. I'm one of creators of Katans. It's Ukrainian Ruby, JavaScript, and C# free school. Currently, I left this school, but it's self-driving. It's still working. And I'm a regular speaker on local Ruby meetups. Cheers to Ruby meditation. Andrew? And here is a list of my social media. Well, we ended up with the most boring part. And let's go with JIT compilation itself. Well, firstly, this slide originally was named How to Speed Up My Ruby App. But just to speed up, it's totally boring. It's no chances to learn, no chances to find out how is Ruby built. And it's not interesting as diving in internals. So, doing live demos during presentation is a bit risky, but I'm generally too risky because I'm doing 2 live demos at the presentation. So let's take a look. Wait a moment. Oh, sorry, 1 second. I need to launch terminal on this screen. Oh, I should switch color schema, probably, because I think no one sees nothing. Thank you. Do you see something? And now probably it's better. Okay. So. At first I tried, I thought that compiling directly on stage will be very interesting, but finished it up with building Docker image. And by the way, you can find it and Docker files on my GitHub on pinned repositories. Repository is named RubyConfBY. So. Currently, it's a very simple thing. I'm just benchmarking. Just benchmarking 2 ways to speed up the code. And we see for regular Ruby, it's like 1,500, and for LLRB version, it's almost 6,000 of instructions per second. It's a very simple benchmark. It's just counting from 1 to 30 millions. Simplest one. And the second thing, well, this will be running a bit later and a bit slower because currently we just had original execution. And the second thing is the implementation of just-in-time compilation, which we will have in Ruby 2.6. We waited for JIT compilation itself. Okay, we're done with it, and now I'll tell what happened. So, and now it's time to tell what happened. What is JIT? JIT, it's just-in-time compilation. In other words, name it dynamic translation. It's technology to improve interpreted languages, to improve bytecode systems. You know, Ruby is built in a way it executes not a real machine code. Your code is transpiled to a bytecode. And in fact, it's for almost every interpreter, like PHP, or like JavaScript, like Python. And JIT compilation, it compiles a piece of application code at runtime, not to instruction sequences of virtual machine, but it turns it to original binary machine code, which is executed directly. So for Ruby virtual machine, it looks like that it executes one super instruction. It used in Java some of JavaScript implementations. For example, Firefox team even have dedicated JIT subteam in it. In .NET, in PyPy, PyPy it's version of Python which is implemented in Python mostly. And really, almost all interpreters. And I need to explain one thing more. Why synthetic test? Well, because real-world tasks really differs. In real world, you will have no chance to create a test which will refer to everyone. So synthetic tests is just enough to show something, to show proof of something working more speedy than regular implementation. And currently, one synthetic test is used widely. It's OptCarrot. OptCarrot is a Ruby NES emulator implementation, and commonly used for benchmarks to prove that something is working more fast than regular Ruby implementation. Okay. So how JIT compilation works? Let's start from the beginning. When you write your Ruby code, you're doing some strings. Those strings are parsed to tokens. Those tokens are built up to abstract syntax trees. You've seen it on previous presentation from Bozhidar. Robocop working with ASTs. After that, Ruby compiler compiling it to instruction sequences, to bytecode. And after that, virtual machine finally executes the code. So in common case, at this process, you lose like from 5 to 20% of time to do this every time. That's why JIT exists. JIT actually discards all those steps, and after first execution and JIT compilation, it turns your code to machine code directly. Which types of JIT we have? It's the most common is and actually the hardest one. It's method-based JIT. It just replaces decided call. So you have some method, your virtual machine executes it, and after this, JIT compiler turns it and replaces it in a call table. Second type is trace-based JIT. It traces execution path of method and turns into machine code the most commonly executed piece. And region-based JIT, it's hybrid of two previous, and actually it's a very rarely used JIT method. Well, explaining about how actually this happens. So we have some object variable. In Ruby, it's structure with some vtable pointer. Vtable pointer, it's a reference to special table which contains references to methods which objects has. Methods are actually references to instruction sequences of Ruby virtual machine, or in case of JIT, to a binary code. And currently I want to tell a bit about JIT history, because well, it's a very extensive thing, and JIT itself as a technology is like 35 years older than Ruby itself. Firstly, it appeared in Lisp, introduced by McCarthy in 1960. After that, it appeared in Smalltalk, made by Sun Microsystems in 1983. So, by the way, self-virtual machine used in this Smalltalk implementation was only 2 times slower than plain C code. Java, of course, and at 1993, at least appeared a term just in time, because previously it was just named dynamic translation. So Ryan Gosling used term just-in-time compilation, and it became famous. Oh, sorry. Oh. Thanks to Microsoft. Нет. Просто вылетело.
Let's go on.
Okay, sorry for this. I am not responsible for Microsoft bugs. Just 2 years ago, after JIT appeared in Java in 1993, appeared Ruby, 1995. And we skipped some part of history here. After that, PyPy was introduced for Python, and it already had JIT at very first implementation. After that, PHP introduced JVM at Facebook in 2011. And why I'm mentioning Python and PHP here? Because in all comparisons, PHP and Python are mentioned as most common competitors of Ruby. And well, it was actually a sort of pain because Python guys said me, we have just-in-time compilation, PyPy is fast. What you can answer? And nothing. And finally, MJIT implementation appeared in Ruby last year in 2017. Why did so late? Why did this happen? It's a sad situation because Ruby core team is actually big, but Ruby compiler core team is actually very small. And Keiichi Sasada, the most known JAR implementer, said at interview on Ruby Keiichi that Ruby actually needs like 100 of compiler developers. So if anyone feel courageous, you can join. I bet that Ruby core team will accept. One more thing. Vladimir Makarov, developer of MJIT implementation, of initial MJIT implementation, said that Ruby C code is mostly similar to a GCC code. Actually, it's not a recommendation. It's a bit of scariness. So, regarding JIT options that we have at the current time. It's a long list, because Ruby has virtual machines implemented in different languages. And for most languages, it's an exception, not a rule. So first one was JRuby. JRuby was originally created by Jan Petersen in 2001 and was just one-to-one port of Ruby 1.6 code. And at this time, JIT wasn't implemented, but beginning from version 1.1, JIT support were added together with Ruby 1.8 support. And JIT in JRuby implementation just compiles Ruby bytecodes to the JVM bytecodes and uses JVM JIT implementation. And it's able to work from version 9 point something. It's able to work with GraalVM implemented by Oracle. And actually, I recommend it if you are working with JRuby, because it's really very fast and eliminates GL as a bonus. The second was Rubinius, created in 2009 by Ivan Phoenix, and this implementation was based actually on a blue book, the design standard of Smalltalk. It implemented principle that PyPy used to implement most part of language in language itself. JIT was math-based, and we had very interesting case in it because Rubinius Ruby implementation has different separate native thread, which actually received calls to turn something to machine code, and it substitutes your original bytecode with compiled one. Okay, next was maglev. For me, it's my most beloved discontinued Ruby implementation because it was a great implementation on the top of Smalltalk virtual machine, and I personally like Smalltalk. And for maglev, it has JIT implementation from Smalltalk virtual machine named Gemstone. Gemstone, unfortunately, is already dead. Maglev is already dead because last commit was 2 years ago. But it has very interesting feature with sharing of code and state across virtual machines. And I totally miss this feature currently. After this appeared actually in 2016, appeared the very first very naive implementation of just-in-time compilation in Ruby, in native Ruby itself. It used very few of JIT optimizations, but it used less memory than standard JIT implementation. And for Ruby core team, memory optimization is a target, not a performance, memory actually. And the optimization branch was never merged and will not be. I can drop you a link to it if you want to do some research how it was implemented. The next try was done by Vladimir Makarov, one of GCC contributor, worker of Red Hat, author of Ruby 2.4 hash tables reimplementation, which actually improved performance of hash tables for like 30%. And with talk about his implementation, he held Ruby KG keynote last year, and he did a really big work. Alexander Lomo on some previous conference references to his work with some description like Rambo commits, because his pull request was really big. He actually converted Ruby virtual machine from stack-based to register-based and added fully functional JIT implementation. MJIT reached 2 times performance of Ruby 2.0, but it was pretty unstable and failed at like 70% of Ruby standard tests. After that, Takashi Kokobun, and mostly in parallel, inspired by earlier Ivan Phoenix work, created manually callable LLVM interface named LLRB. It's a gamma which can be used to compile code that needs optimization in manual mode. It uses specially patched version of Ruby 2.5, and but it's not extensively patched, just exposed some C constants needed for LLRB. And it supports almost all YARV instructions. And still working for Ruby 2.5. And the last one implementation that we will have in Ruby 2.6, it's MJIT YARV. It's based on earlier Makarov's work, but Takashi, who made LLRB, decided to take Makarov's work and revert changes which touched virtual machine. So actually, virtual machine left stack-based. So some JIT optimizations were turned off, but this made JIT a bit slower and results of JIT a bit slower, but much more stable. It was merged on Ruby trunk at 4th of February this year. And the greatest news is that this branch is able to launch Rails without failing. Now I will show you some more demo. Hope this time it will not fail.
Let's go.
Okay. So. First of all, I want to show how benchmark for LLRB looks like. So we have two methods implemented into two anonymous class, and they do just very simple thing, counting from 0 to 30 millions. When you need to optimize some code with LLRB, you are calling LLRB JIT compile, passing by class and class itself and method in it. But by the way, you can enable it globally by instruction LLRB JIT enable. And after that, we'll be able to compare. So currently I'll show you something really interesting, but I need to copy. Oh, crap. Okay. So, do you know about RubyVM instruction sequence interface? Great. Yeah. Well. Yeah. So here we see the very internals of Ruby code. It's a instruction sequence of Ruby code that counted. We can just throw off all traces and leaves, and left with really meaningful to put something to stack, plus it, and do this 30 million times. And now I want to show how it will look like when you try to decompile LLRB implementation. Just call the function. But how it look like as a C code? Oh, very simple. Okay, here I have very simple script with which just adds 2 to 2 10 million times. Okay, it will execute silently without any output. I will got to put some puts in it. It doesn't matter. And let's take a look. 15. Crap. It's hard to see it from this. Thank you. So, what actually MJIT does? It takes the meaningful flow of instructions, of Ruby virtual machine instructions, and just turns every instruction into a C code as a label. And the mostly interesting thing is that we have a very strict check here. We check call stack, and if we not code from expected place, we will just leave to fail silently. And okay, and now about some numbers. So, plain Ruby had almost 2,000 of instructions per second. LLRB had 5,500, and MJIT had almost 6,500 instructions per second for this very simple benchmark. But for the real world, I already tested it in a real-world application, and well, natural increase of performance was not more 15%. And actually for 2.6 without JIT optimization, sometimes it was even faster. So it's a long way, and we are at the very beginning of it. It was merged into trunk, and will appear in 2.6 pre-release. And the merging of this was actually the hardest part because it was a very big commit. And Ruby core team spent a lot of time and ended up with cherry-picking commits from MJIT YARV branch to get this into trunk. Thank you.
Thank you. We have time for 2 questions. One question right here. Let's wait for microphone. Right there. Okay, let's start from this one.
One?
It was next one.
Okay, thanks for your talk. Quick question. As you showed us instructions, and there are trace points which debugger use. Have you any idea how will debugger now work if we compile our code, and are there any work on that?
Sorry, repeat please, last part of question.
Are there
just
any work on that right now in Ruby community?
Well, not sure that I get question correctly, so maybe you try to reword it.
Okay, you showed instructions, and there are trace points.
Yeah.
Yeah, which debugger use, so you can go through
do you
points?
mean about live debugging of JIT?
Yeah. Right.
Well, actually, you are not able to. But you can save dynamic libraries compiled SO files from those C source code, and you can place GDB breakpoint in it. So if you are using JIT, you achieve GDB as a debug tool in the present.
Thanks.
Sorry for that.
Thank you for your talk. Quick question. You mentioned Grail from Oracle. Have you compared JIT implementation with it?
It differs from depends on test which we are using for performance check. Because it works really very nice and very fast for OptCarrot, but is much slower for Rails, for some Rails application. So it depends on a problem domain you want to use Ruby.
And last question. To try it out, so as far as I understand, you mentioned that it's in trunk currently. Is it available as, I don't know, the 2.6.dev release, something?
Yeah, it's already merged and will appear in pre-release.
When?
I don't know, but as a tradition, Ruby, a new version of Ruby appears near Christmas. So hopefully at the end of this year.
Okay, thank you.
Thank you. Yeah, one more question here. Have time.
Yes, thank you. So thank you for your talk. It was most interesting. I would like to ask you one short question. You had mentioned that there was some stability gains as you had developed, but there were minor issues. Could you please throw us some numbers? So, for example, stability gains, what do they mean? What was the required stability and what was the gain? Well, just approximately, thank you.
Okay, regarding stability, if I heard correctly, yes. Regarding stability, we have a complicated thing because Ruby itself contains a number of tests, so like 90,000 as far as I remember. Which actually describes the behavior of Ruby according to Ruby standard. And Ruby itself passes all of them with native implementation, yeah. It was predictable. MJIT at first implementation failed near 30% of it. MJIT YARV doesn't fail anything. So currently, we can count it as a stable implementation of JIT. But it's still not recommended to enable in production environment.
We'll get there. Thank you.